Hello. Okay. Just wait one more minute for the people to join. All right. So welcome. Just introduce me. So yeah, I am Sai Dinesh, PMRF TA for the DSP Digital Signal Processing course, and welcome to week 5 of doubt clearing session. Just- Sorry, just right. Week 5. All right. So in this week, I'll be covering some basics of uh, Z transform and properties of Z transform. Next, I'll be moving to the um, uh, yeah, okay. So properties of Z transform. I'll be talking about linearity, time shifting, reversal, multiplication, etc. and etc. So let's just get started. I think from the last lecture, I have actually introduced Z transform already. So for a discrete time signal, uh, let's say we have a discrete time signal x of n, which is discrete time, and we have a Z transform x of z is equal to n equal to minus infinity to infinity x of n z per minus 1, right? So this is the Z transform. I mean, with the notationally we write it as x of n capital X of z. If so, this here z is a complex number where z is equal to r e per j omega. If z is equal to e per j omega, x of z is equal to overall n x of n e power j omega whole power n, which is equal to dtft of x of n, right? So this is Z transform and the dtft of a signal. So basically we have seen that a signal does not always converge. Does not always have DTFT, meaning the DTFT of a signal does not always converge. So we come to a generalized, more general way where R into e per j omega, where R is a magnitude. So as now we talk about a generic z. Okay, and since mod of z is equal to mod of r e power j omega is equal to r, the z is usually mentioned as a unit, like in the form of circles with the real part of z and imaginary part of z, right? So these are the basic signals, and then we have seen that a few examples where if x of n is a power n into u of n, then x of z is 1 by 1 minus a z inverse by mod z greater than mod a. And then when x of n is a power n u of minus n minus 1, same x of z is again the same, but then mod z is less than mod a. So these are the ROC, the region of convergence. So this is a right-sided sequence, and this is a left-sided sequence. So commonly the right-sided sequences have ROCs of the form I mean, okay, let's just try the properties, like a few properties of the Z transform, ROC of the Z transform. Is it recording? Hello, hello, yeah. So properties of the ROC of the Z transform. Okay, so property 1 would be ROC will either be of the form of the form 0 less than RR less than mod Z less than RL less than or equal to infinity, right? So so it's like some RR, some RL, sorry, or mod Z less than RL less than infinity, right? Of this form, like if it's a left-sided sequence, then this will be the region, or if it's a right-sided sequence, then this will be the region. So in that case, so and then ROC, the Fourier so like property 2 would be the Fourier transform of x of n converges if and only if the ROC of the Z transform of x of n includes the unit circle, right? And then property 3 would be ROC cannot contain any poles. Okay, and then there are a bunch of different other properties where, like, if x of n is a finite duration sequence, then we have the ROC as an entire Z plane except for z equal to 0 and z equal to infinity. And then if r x of n is a right-sided sequence, then the ROC extends outward from the outermost pole, and then if x of n is left sided sequence, the RO sections invert from the innermost pole. So other properties, right sided sequence, an ROC extends outward from the outermost pole, and for left sided sequence, ROC extends inwards from the innermost pole. So next I want to talk about a few of the Z transform properties. Okay, for this, let's do an example, right? So no, if x of z is the Z transform of x of n, derive the Z transforms for the following signals. So first one would be x of minus n, right? So that this way x1 of n, so x1 of z is equal to sigma of x1 of n z per minus n for all n, which is equal to x of minus n z per minus n for n equal to minus infinity to infinity. So if we do a change in the variables, then we have k equal to minus infinity to infinity x of k z per k, which in turn can be written as k equal to minus infinity to infinity x of k z per minus 1 power minus k, right? Now we know that x of z is equal to n equal to minus infinity to infinity x of n z per minus n. So if we compare, and then for example if we have ROC for alpha less than z less than beta, then right, so this is the ROC, then this has ROC. So now we know that x of minus n, exactly if we see z, this actually corresponds to z inverse, which means that the Z transform of x of minus n is x of z inverse. Again, the ROC is also of the form alpha less than mod z1 z inverse less than beta, which implies 1 by beta less than mod z less than 1 by alpha. So this is for the x of minus 1. So let's take x2 of n is equal to x star of n, which implies x2 of z over all n equal to minus infinity to infinity, x star of n into z power minus n, which is equal to, bring out the conjugation here. So n equal to minus infinity to infinity x of n z star of minus n of whole star. So this conjugation and this conjugation and this conjugation will negate each other. So this will be x star, and then z star minus star whole star will be z power minus n. Right? Now if we see, so let's just bring it, since it is a summation, it's a linear operation, we can do this. Alright. Now this here is x of z star, and then we have a whole star, which is equal to, which implies x star of z star. Therefore now we know that x star of n is a z transform pair with x star of z star. So if you talk about the ROC here, alpha less than v star less than beta, which again alpha less than mod z less than beta. Therefore it is no change in ROC. This is another property. So for a time reversed version, we have a x of z inverse. So for a time reversed version, x minus of n, we have x of z inverse. And then for the conjugate version, x star of n, we have x star of n as a transform pair with x star of z star. So now let's do the third example, where we need to find the z transform for x of n minus n naught. Let's say this is x3 of n. Now x3 of z is equal to n equal to minus infinity to infinity x3 of n z power minus n, which is equal to n equal to minus infinity to infinity x of n minus n naught z power minus n. Now what do we do here? Again we need to bring it to the form of x of n into some other z tilde. So now we apply change of variables, where m equal to n minus n naught, which implies n is equal to m plus n naught. Right? So this will be equal to m plus n naught is equal to minus infinity to infinity x of m z power minus of m plus n naught. No, but this doesn't actually change anything since this is from minus infinity to infinity. So therefore this will be m equal to minus infinity to infinity x of m z power minus m, and then we bring out this n naught term to the outside, since m does not belong. Okay, let's write it in another step, plus n naught Now this n naught does not belong with m. So what we do is m equal to minus infinity to infinity z power minus n naught x of m z power minus m. We see here this is equal to x of z. Therefore x3 of z is equal to z power minus n naught into x of z, which implies x of n minus n naught is a z transform pair with z power minus n naught into x of z. So this is a very interesting property. Right, so this is the shifting property. Here the ROC equal to Rx except for the possible addition or deletion of z equal to 0 or infinity. So the ROC actually does not change much, except for there might be an addition or deletion of the poles and zeros at z equal to 0 at 0 and infinite. Right, so okay, so I'll just talk about all the properties first, and then maybe we'll talk about the examples. So next D part is x4 of n is equal to z0 power n into x of n. 1 second. Z0 power n into x of n. So where z0 is a complex constant. Right, so x4 of z is equal to n equal to minus infinity to infinity x4 of n z per minus n, which is equal to n equal to minus infinity to infinity z0 power n into x of n into z power minus n, which is equal to n equal to minus infinity to infinity x of n z by z0 per minus n. Right, so this again is the form of x of z by z0. Therefore the new x4 of n or z0 power n into x of n is a z transform pair with x of z by z0. If we talk about ROC here, so the new ROC will be alpha less than or equal to mod z by z0 less than or equal to beta, which implies alpha times mod z0 less than or equal to mod z less than or equal to beta times mod z0. So basically, depending on z0 that we are multiplying here, the magnitude of z0, it is either a shrinking or an expansion of the z transform. In case if z0 is some e power j omega naught form, then it is a rotation of the Z transform. Z transform poles and zeros, right? So this can be either interpreted as a scaling or a shrinking, and that is pole zero locations change along the the radial lines of the z plane. So if z0 is complex, as I said here, the complex with unity magnitude, so that the scaling corresponds to a rotation of the z transform by an angle of omega naught. So the poles and zero locations change in positions along the circles centered around the origin, right? So the the equivalent of this is e power j omega naught n into x of n is a Fourier transform pair with x of e power omega minus omega naught. Okay, so this is one more, and then the final one here is that we'll be doing here is equal to n times x of n, which is equal to x5 of n, let's say. So x5 of z is equal to n times x of n z per minus n from n equal to minus infinity to infinity. So how do we go about this? We have an n here, but then we would like to remove that n, right? So let's do the differentiation here. So let's say we have x d of x5 of z by dz is equal to n equal to minus infinity to infinity x of n minus n into z per minus n minus 1. So this is equal to minus n into x of n z per minus n z inverse. So if we bring the z inverse outside, minus z inverse minus infinity minus n x of n z per minus n. Exactly. So if we see here now, this part, so this is d into xyz by dz. So if we bring it this side, this will be equal to minus z times dx5 of z by dz is equal to n equal to minus infinity to infinity n times x of n z per minus n. So which is what we wanted to find here anyway. So what we know is, what we finally understand from that step is n times x of n is a z transform pair with minus z into dfxc by dz. So yes, and then the ROC here also does not change actually. So these are a few of the important I mean, here we highlight some few by doing these examples. Here we highlight few of the important properties of the Z transform. Here we know the multiplication property, then we get the multiplication by an exponential sequence, and then conjugation, time reversal, time shifting, etc. So all these properties are quite important while solving the problems that we face. Alright, so these are the properties that we face. that we come across. And then there is one more property called the linearity property that I didn't discuss here. Uh, so the linearity property says that, so there is only one property that is left, which is the linearity property. It states that if x1 and x2, so I'll write it in simple forms, which is a times x1 of n plus b times x2 of n, and this is equal to a times x1 of z plus b times x2 of z, and the ROC contains region of ROC of x1 and ROC of x2, which is the at least the intersection can be larger, right? So yes, we can do a few questions. So let's do one more example. This is a different example. So we need to prove that x of 0 is equal to limit z tends to infinity of x of z only when x of z is causal. So this is the question. So we need to prove. So this is actually called the initial value theorem of the z transform. So this is known as the, just write it down, initial value theorem of z transform. So if x of n is causal, then x of n is 0 for n less than 0. Therefore, it intuitively says that x of z is of the form x of z is equal to x of 0, x of 1 z per minus 1, x of 2 z per minus 2, and so on. Now this limit z tends to infinity x of z will give x of 0, 0 plus 0 plus 0. So we prove that limit z tends to infinity x of z is equal to x of 0 when x of n is causal. This is the initial value theorem. Let's do cache. So let's do one more example. Okay, so x of n be a left-sided sequence Okay, that is 0 for n greater than 0. And given in the question that if x of z is equal to 3z inverse 2z power minus 2 by 3 minus z inverse plus z power minus 2, then find x naught. Find x naught. Oh, I didn't realize my. So x of n is a left-handed sequence that is 0 for n greater than 0. So like anti-causal signal. And then if we have that x of z is equal to 3z inverse plus 2z power minus 2 by 3 minus z inverse plus z power minus 2 given x of 0. So now this signal is of the form C B A 0 0 0 and so on. So this is for the 0th sample n equal to 0. So x of z will be of the form x of 0 plus x of minus 1 z power 1 plus x of minus 2 z power 2 and so on, right? So x of 0 is equal to limit z tends to 0 x of z, simply. So then these parts go to 0, which is equal to limit z tends to 0 x of z is 3 z inverse plus 2 z power minus 2 by 3 minus z inverse plus z power minus 2. Now take the z power minus 2 common. Just like, since we cannot simply put z power minus 2 here, if we take z power minus 2 common, 3z plus 2 by 3z square minus z plus 1. Now if you put z tending to 0, this is equal to 2. Therefore x of 0 equal to 2. Right? All right. Let's do one more example which talks about the properties and the relations between x of n and x of z. Right. So 1 second. So let's say we have let x of n be an absolutely summable sequence n equal to minus infinity to infinity mod of x of n less than infinity with the rational z transform. Okay, so if x of z has a pole at z equal to 1 by 3 and limit mod z tends to infinity x of z equal to 1, what can be said about the extent of x of n? What can be said about x of n? One second, let me just check if this is a question in the assignment. Okay, then I guess this is not. So talk about finite. Is it finite or and is it left sided or right sided? Okay, so yes, so here we go. So we need to use all the information that we have. I mean, there is one piece of information where pole is at z equal to 1 by 3, and then we know that it is absolutely summable, right? So with these two points, we can say that when there is a pole at x equal to 1 by 3 and absolutely summable, therefore ROC includes the unit circle when this part corresponds to this, also given x of z converges at z tending to infinity, right? Now can it be a finite length sequence? No, because x of n has a pole at z equal to 1 by 3. Right. No, so like can be a finite no. X of n has a polet z equal to 1 by 3, and then it says that it includes the z trans, it includes the unit circle, so it must be the case must be the case that it should be somewhere in this region. So so can this tend to infinity, or will this be will this be bounded by uh, another region? And then can it be anti-causal sequence? No. No, because 1 by 3 is less than 1 and ROC includes unit circle, therefore it is a causal signal. If it is a causal signal, it can be a right sided sequence. Okay, yeah, so that is what we can say from the information that we have in the question. So there are okay, maybe I'll go to the assignment questions next. Okay, assignments week 5, just give a 1 minute break. So we have the assignment 5. Now y of n is equal to a1 x of n, now x1 of n plus a2 x2 of n, and then this is the linearity property that we have. Question 1 is about linearity property, and then I have actually talked about RAC earlier. It should be the intersection of the two x1 and x2. So now there is a delay in time domain resulting in both scaling and rotation in the Z transform. Again, this is one of the properties that I've just talked about. The third one would be x of n and x of z be a Z transform pair such that e power j omega belonging to ROC of x of z. So it is of unit magnitude but with an angle of omega. If y of n is equal to x of minus n, then e power j omega must necessarily belong to the ROC of y. So question 3 is x of n, then x of z, e power j omega belongs to the ROC of x. Belongs to the ROC of x. Now y of n is equal to x of minus n. So this actually has, according to Z transforms properties, x of n is a Z transform pair with x of 1 by c. So if e power j omega contains ROC of x, and then this is y of z, this contain e power j omega. So we have seen that ROC of the time reversed signal actually has 1 by rx. So the poles and the zeros according to in the radial directions get reciprocated, like 2 will become 1 by 2 and 1 by 2 becomes 2, similar way. So if we have the Z transform property and then this is the ROC property, will this include e power j omega? So this is the question. And question 4, sorry, if x of z is non-zero for minus omega less than omega c, for omega c then x of n belongs to R. For minus omega c less than omega c. So we know that according to inverse dt of t, s of n is equal to 1 by 2 pi, minus pi 2 pi x of n e power minus j omega n, x of e power j omega into e power j omega n into d omega, right? But then it is non-zero only for in this range. So 1 by 2 pi minus omega c to omega c x e power j omega n into d omega. All the parts included, or did it get okay. I don't understand what's wrong. Okay, there was some bug with the app. So here he said that it is non-zero, but it didn't belongs to R or C. He did not say anything about that. And then this is a complex exponential. So will this be a, will this belong to R? Need to figure out. Okay. So next question will be, the magnitude x of n belongs to R, then the magnitude is odd symmetric and phase response is even symmetric. Now again, this is from the properties of the DTFT which we have discussed in the previous class. I mean, properties of x of z when x of n is real or x of n is imaginary or even odd. It has been discussed. So it's pretty straightforward. You just need to look at the the properties. You will figure that out. And next question. One second. Sorry. So here the question is that a system with input output relationship described by an LCCDE has a rational transfer function, true or false? Is it so an LCCDE, what question is that? Question 6. LCCDE, a system with LCCDE can be written as Fn is equal to minus of k equal to 1 to n ak by a naught yfn minus k equal to 0 to n bk by a naught x of n minus k, right? So if we apply the z transform here, this will be y of z is equal to k equal to 1 to n ak by a naught z per minus k y of z plus k equal to 0 to, this is equal to m, so 0 to m bk by a naught z per minus k x of z, right? Now solving for yz in terms of xz, we get y of z is equal to k equal to 0 to m bk z per minus k ak equal to 0 to n ak z per minus k into x of z. So this actually is the h of z. Therefore, I think this can be solved. So let's actually remove this part from the lecture notes. Sorry. Yeah. We get some y of z now. Seventh question says that if x of x of n is equal to 1, what is the z transform of x of n equal to 1? So just apply the z transform formula. X of n x of z is equal to sigma x of n z power minus n, we get summation from n equal to minus infinity to infinity z power minus n. Just need to solve the geometric progression to get the output for that. So for the 8th question, x of n is equal to n square a power n u of n. Eighth question is x of n square a power n u of n. How do we solve this? No, we know that a power n u of n has 1 minus az inverse. Now how do we get this from this? So we get a into a power n u of n, find x1, and then n times x1 you get x2, which is the final one. So we know that
యాంటీ క్లాక్ వైపు తిరగాలి, మళ్ళీ కాసేపు తర్వాత మళ్ళీ క్లాక్ వైపు తిరగాలి ఆటోమేటిక్గా.
so we know the property of if x of n belongs to x of z, then n times of x of n belongs to minus z times dx of c by dz. So basically just need to apply it twice here and get the final answer, right? And so 9th question. Question 9. A system's transfer function h of z is equal to b of z by a of z such that the summation of minus infinity to infinity mod h of n is then equal to infinity. Furthermore, all roots of a of z lie inside the unit circle. Okay, so what are the following statements are true? So he's saying that it's absolutely summable, and then the roots of a of z lie inside the unit circle. So root is somewhere over here, but then since it is absolutely summable, it should include the unit circle. So if the pole is here and if it needs to include the unit circle, what is the property? Pole inside unit circle, that ROC should include unit circle. What is the property of h of the h of n, right? So now this is the, I mean, from here we need to, like, this is the main information that we have in the from the question here, the absolute summability and also the roots inside the unit circle. From this it's pretty straightforward to find the ones which satisfy the options in the question, right? So next one is the 10th question. Identify the properties that apply to the sequence whose z transform x of z So x of z is 1 plus z power minus 2 by 36 minus 24 z inverse plus 13 z power minus 2. And you also said that mod z greater than root 13 by 36. So if we take this equation and solve it, we get the roots to be z inverse minus 12 minus 18 I by 2 into z inverse minus 12 plus 18 I by 2, somewhere around this part, I'm not exactly sure. So yeah, so this actually has that. So now the poles actually have the magnitude this one. I mean, once you solve this, you get poles to be of, these poles to be of this magnitude here, but then root 13 by 36 is less than 1. Correct? So root 13 by 36 is actually less than 1. And the ROC includes all values of z which are greater than this, that is the outside of that pole. So we know that there is a pole inside the unit circle, and then the ROC is outward from that pole. What are the properties of the signal? What are the properties of the signal? That is the question. So I think I've done it until the 10th part. 11 is actually pretty straightforward. You need to know the properties of the signal, and then the 12th one, just do the 12th question. Question 12, it is given that the system is causal and stable, right? And oh, right. And then it said that there are 4 poles and 4 zeros at 0, and then 4 poles which are plus or minus 0.5 plus j into plus or minus j 0.5. So these are the signal that we have. So h of z will be z power 4 by z minus p1, z minus p2, z minus p3, z minus p4. No, what did he say? G of n. Okay, so not solving the exact question, I'm just doing a similar question where the values are actually from 1 by 2 plus or minus 1 by 2. Here we are in the question it contains 1 by 2 root 2, 1 by 2 root 2, but I'm just taking it as 1 by 2 1 by 2, which is how you similarly solve the question. So if we multiply it by an exponential, so it's saying that So I'm doing the question where g of n is e power j pi by 4n into h of n. But we know that, so if z naught is e power j pi by 4, then g of n is z naught power n into h of n, which implies g of z is equal to h of z by z naught, and ROC is mod z naught times the actual ROC. So once you know this property, just have to like, so therefore the poles are, but then here the magnitude equal to, therefore there is a shift in the poles and zeros by angle of pi by 4 basically. So once you shift the poles and zeros to the angle of pi by 4, finally what we have is after shifting it, they will be in here on the axis. Now actually the transfer function is actually reduced by a lot. So once we get the transfer function, so simply we need to substitute the values. When we know the now we know the, so we know the actual poles, we shift them by pi by 4 minus pi by 4 in this case to get the new poles. Now we know the new poles and zeros, we find the transfer function and then substitute all these values to get the values of, I mean to get the answers for 12 to 15. So basically these are the hints for these solutions, and then I have discussed a few of the examples from different sources. So yeah, just